Okay, hi everyone and welcome to today's 1W Minds Talk. Today's speaker is Kathlén Kohn from KTH Stockholm. She obtained her PhD from the Technische Universität Berlin in 2018 and has since been a postdoc at both Brown University and the University of Oslo before joining KTH as an assistant professor in 2019. Her research blends algebraic geometry with practical applications, such as computer vision and now also machine learning. The latter is what she will speak about today in the talk named Understanding Linear Convolutional Neural Networks via Sparse Factorization of Real Polynomials. The floor is yours, Kathlén.
Yes, thank you very much for this very nice introduction and the invitation. Yes, so I am trying to deliver like a slow-paced talk here. So if people have questions, I'd be happy if they feel comfortable with the recording to just interrupt me. That's perfectly fine. I don't need to specifically need to get to the very last slide of this talk or something like that. Yes, so let's get started. Maybe go back one more time. So this is joint work with Guido Montufar, and who is more a machine learning theory expert than me, and Matthew Traeger, who is now working at Amazon, and then my very talented PhD student, Vahid Shaverdi. And so Vahid and I were maybe more the algebra people on the team. Okay, so let me repeat so that we have the same notation. What I understand under a feed-forward neural network. I'm not going to give a very formal definition here, but in a kind of abstract sense, every such feed-forward neural network parametrizes for us a family of functions. And so here I'm using, as I said, this mainly to fix the notation. So here theta is the parameters that you're going in to find when you train a network. So these are often called the weights, and sometimes there's also biases and so on, all the parameters. These are collected into this vector theta. And then you have L layers in such a network. Each layer gives you a function that depends on this parameter theta, and then composing all these layers together, you're getting an end-to-end function. Okay, and so this is all encoded in this map mu here at the very bottom of the slide. So mu is the network parameterization map that eats all the parameters, and then it spits out the end-to-end function. And a very important player in this talk is the image of this map. So M is sometimes called the neural manifold, or just called the function space, which is simply the set of all end-to-end functions that a given network can have, or more, maybe better said, a given network architecture can have. And again, if there's any questions about any words that I'm using here or notation, and please ask. Okay. And so why is this important to think about this network parameterization map and to think about these neural manifolds? Because in the setting of supervised learning with neural networks, we have given training data D and some loss function that we want to minimize. And in fact, the loss function is typically looking like here on this slide. It's a composition of the network parameterization map with a loss that you sort of define on your space of functions. And so in machine learning, when you actually train a network, you're solving this composed minimization problem here. But there's many geometric questions that arise in this setup. For instance, if you change the network architecture, then how does this affect the geometry of this neural manifold, M? Okay. And then it seems very intuitive that if the geometry of this guy in the middle, M, changes, then this optimization problem of training the network is also going to be affected. And the question is how? So I'm thinking of it in like a two-step situation. can we understand the geometry of the neural manifold in terms of the neural architecture? And then can we, in the next step, understand how this actually has impact on our optimization problem? Okay, and so this is a very, very general framework. And in this specific talk, I'm going to focus on one tiny little bit of this geometric question, namely, how can I or what can I think happens when I change my network architecture from consisting purely of fully connected or called dense layers to convolutional layers? Yeah, so then how does the geometry of the function space change, and how is that going to impact the optimization problem? So this is the question I'm going to address here. Okay, and so I want to answer, of course, in the end, this question in generality. Can I say what is exactly the effect of working with convolutional layers instead of dense layers? But in our very first study, we did this very concretely for the case when our networks don't have any activation function. Yeah, just to be able to do every calculation explicitly on paper, and you can actually prove things. But then you can compare these linear fully connected networks with linear convolutional ones, and you can see exactly what's going to change. And okay, so let me focus on these linear networks and to maybe repeat what this means. So a linear dense network, this network parametrization map is now something very, very easy, because each layer is a linear map given by a matrix, and the sizes of the matrices are given by the number of neurons in the layers. And so the network parametrization map takes the matrices in the layers and multiplies them. So here in this example, I am multiplying a 3x2 matrix with a 2x4 matrix. And then I get a 3x4 matrix, and I'm not getting all 3x4 matrices like that. I only get those that have rank at most 2. And because this middle layer, the bottleneck layer, gives us this rank constraint on the linear map. And that's in fact an if and only if. So the neural manifold is in fact equal to these rank bounded matrices. So that's the baby example. And you can easily generalize this baby example to linear fully connected networks with many, many, many layers, because the network parametrization map, it just takes all these matrices and multiplies them. And the neural manifold is going to be linear maps that have bounded rank, and the upper bound is just the bottleneck layer, so the width of the smallest layer, if you want. And so algebraic geometers are very excited when they see this guy, this neural manifold, because this is a very classically studied algebraic variety, and we know everything about it. Okay, so we like it. Now would be a good moment if there's a question. Otherwise, I'll move on to the convolutional case. So in this fully connected case, again, it was easy to compute this neural manifold, and it was something which is called an algebraic variety. If you do not know what that means, it's not a big deal. Algebraic variety for me here means simply that the set itself is the solution set of a bunch of polynomials, which is here just the minus of the matrix. So I can describe this, I can send this neural manifold to you via email by sending you a bunch of polynomials, and the solution set would be the neural manifold. Now, this is not going to be true anymore. I cannot just send you polynomial equations if you change from dense layers to convolutional layers. So in this talk, I'm going to focus on sort of convolutions on one-dimensional signals, just to have easier pictures, but many things carry easily over to the higher dimensional setting. So if I have a convolution on one-dimensional signals, then the graph of the neural network, it would not have, well, dense layers anymore, but sort of sparse layers, and also with weight sharing. So the edges here in the pictures that have the same color, they share the same weight. So that means that now our matrices that encode the linear maps in each layer, they are not arbitrary matrices anymore, but they are of a very special form, as here shown on the slide. So they have this interesting property that they are kind of triplets matrices, but with higher stride. So in the triplets matrix, each row is a copy of the previous one, and then you shift it once to the right. But here I might shift more than once, and that's called the stride. Okay, so in general, the network parametrization map is now going to multiply many of these generalized triplets matrices together. And since generalized triplets matrix is such a long word, I'm simply going to call them convolutional matrix, okay? And the non-zero entries in the matrix are called the filter, which is here simply a vector because I'm dealing with one-dimensional convolutions, and the stride S, which is sort of how fast the filter moves through the signal. Okay. Now I have to tell you one technical slide, unfortunately. So bear with me, or just ignore it and wait for the next slide. But to state something mathematically precise, I have to walk you through it. But the main message is very easy. The main message is that the multiplication of convolutional matrices is equivalent to multiplying certain polynomials. And this is, I think, a well-known fact in signal processing, that if you compose a bunch of discrete convolutions, then that's the same as some polynomial multiplication. So here's how this works. Okay, so it's a basic fact that you can do in your linear algebra class, that if you here look at this network parameterization map that eats the filters W1 through WL, and then it multiplies these convolutional matrices together, that you're going to get another convolution. And it's easy to compute the stride of this target convolution. It's just a product of the previous strides. Now the question is, I can easily compute the stride of the end-to-end convolution, but since it's a convolution, it also has a filter. So what is the new filter? And my favorite way of computing it is via this polynomial multiplication trick. So to do that, I have to, here is the technical part, I have to introduce another map, which looks a little bit scary, but it's actually something very easy. So now think of capital S as a brand new integer that at the moment has nothing to do with any strides, so it's just an integer. Then the map pi S, it eats a vector, v, and then it just takes this vector to be the coefficients of a polynomial. Okay, but I am going to choose a polynomial in a very specific way, as you see here. So all the monomials that appear, they are always sort of, it's more like a polynomial in x to the power of s than just a polynomial in x. Yeah? So it's of degree k minus 1 in x to the power of s, if you want. And so I'm taking all of these terms of degree s times something and write down these coefficients, and they are my vector v. Okay? So just think of any vector as a coefficient vector of a polynomial, but it's a sparse polynomial because if s is very, very large, then you're just going to have very sparse terms here. And now comes the important formula. Namely, this yellow part here is what I had already said in words. What's happening on the left is that on the left, there is a bunch of filters, W1 to WL. The map mu multiplies the convolutions together, and then pi1 just takes that end-to-end convolution that we're interested in computing and writes it down in the most standard way as the coefficient vector of a polynomial. And that polynomial is in fact equal to a product of polynomials. And here's something interesting happens. So for every filter, you write down a polynomial using this map above, and the capital S is always going to be the product of the previous strides. Yes, this is a fun exercise if you want something to do on your way home or on your lunch break or whatever your next downtime is. Yeah. So the message overall is that composing these convolutions is the same as multiplying polynomials, but they are sparse polynomials. Because I always have these capital S's, which are the product of the previous strides. And so, since I am an algebraic geometer, I love polynomials. Okay, and so I just completely rethink my network parametrization map, not anymore as sort of the map that eats filters and then multiplies convolutional matrices, but I'm just now, I can simply think of it as that this map eats these sparse polynomials and then it multiplies them. So that's now an equivalent way of thinking about the network parametrization map of a convolutional network. And that works in higher dimensions as well. You just need more variables. You cannot deal with anymore with a single variable x. Okay. So linear convolutional networks multiply polynomials together. That's what they do. Okay, here is the reminder, writing down the same thing again. And then I can tell you a very first theory on what is now the neural manifold. Using this approach, one can, with basic algebraic geometry, see that this function space, this neural manifold, is now something we call a semi-algebraic set, not an algebraic variety anymore. That is Euclidean closed, and we also know its dimension. So I guess you know all the words here except maybe semi-algebraic. Semi-algebraic means that to describe the set, again, if I want to send it to you via email, how can I do that? I want to send a neural manifold to you in an email, then it's not enough to send polynomial equations. I also have to send you polynomial inequalities. That's what semi-algebraic means. It's a solution set of a bunch of polynomial equations and also a bunch of polynomial inequalities. Okay, and here is just some sort of pictures that show low dimensional slices of function spaces in two specific settings. So you see that these are kind of funny objects. And for instance, on the picture on the right, I have marked this dashed boundary. That would be one of the polynomial inequalities that I would have to send you via email. That would cut off this yellow surface along that curve. So there is a first sort of difference in convolutional networks and dense networks, namely what type of animal even is its neural manifold, which is going to be very important for the type of optimization problem that we're going to solve for retrain. Okay, let me tell you one easy corollary before I do actually a summary slide. From the theorem, we can also compute the dimension of this neural manifold. Computing dimension is interesting because you can compare the number of parameters you have with the dimension of this, and that gives you how much sort of a given network architecture over parameterizes, right? Like the difference of the dimension of the parameters minus this dimension tells you that. And another thing is this dimension also tells you how you should think of this optimization problem again. Because in very special, or like in the situation when all the strides are equal to 1, which might be the most naive choice of building a convolution, choosing all strides equal to 1. And that's the only situation when this neural manifold is a full dimensional subset of its ambient space. So here, let me tell you a summary slide. I've talked about linear dense networks where the neural manifold is a variety defined by polynomials, equations. And then I write LCN for linear convolutional networks. And they're always semi-algebraic, so I need also polynomial inequalities, and they're also Euclidean closed, at least, so the boundary is there, and the boundary is going to be important in the optimization problem, of course. And then we can still distinguish these two cases if all the strides are 1 or not. And in one situation, we have a full dimensional subset, and otherwise we have a tiny dimensional thing. So why might that be relevant? I'm just trying to make a sketch here, okay? So imagine you have an optimization problem in the plane, and your semi-algebraic full dimensional subset is what I'm trying to draw here. It's the kind of something like the unit ball of the 4 norm or something like that, okay? Now, no matter which optimization problem you're solving, given some data X outside of this green semi-algebraic set, you are going to land on the boundary of this semi-algebraic set. Okay, and that is also now going to be true in the machine learning setting when you're dealing with a linear convolutional network where all strides are equal to 1. You're going to have a picture like this, and no matter what your loss function is that you're going to minimize, you kind of want to land on the boundary of this set. I hope that makes sense. Yeah, so this is what I'm saying here. So the same sort of picture applies when you train a network and you minimize the loss function of this form. Okay. And it's in fact something that you can prove formally if you want, that you know, the critical points of your loss function, they typically land on the boundary, unless you already started essentially from the interior or something goes wrong. But yeah. Okay, so on the other hand, let me see. So what we agreed on so far, I hope, is that in this middle column, you typically have a non-empty boundary, and you're in fact often going to land there when you train a network, and hence it might be interesting to understand this boundary. Now, this is very, very different if I'm sending you an actual algebraic variety, like in the linear dense case, because it doesn't have a boundary. The boundary of an algebraic variety is empty. So I can actually never, it's completely irrelevant for obvious reasons in the situation of training a network. So you see how this, just the fact of asking what type of animal the neural manifold is going to change the optimization problem quite drastically. But there's other special points on an algebraic variety that can play a role when you optimize a function over it. For instance, we have so-called singular points on a variety. If you do not know what this means, it's not a big deal. A singular point is a point where a variety does not look like a manifold. So there's sort of a theory that almost everywhere a variety just looks like a manifold, but at special points it might not, and these are sort of the singular points. And these singular points, depending on how exactly they look, they can be sort of more exposed in an optimization problem. And in fact, they often are, even in the setting of training a network. So I guess many people here in this audience are aware of the Netflix problem, yeah, which was essentially the problem of, you know, finding like low rank approximation, like given some partial matrix or something, find a matrix of low rank that approximates it. And when you ask for something like this, say you want a matrix of rank 9, and it's a huge, huge data that you have given, then in fact it might be that often this algorithm you run returns a matrix of even lower rank, namely 7. And all these situations where you happen to have get a lower rank than for what you asked for, these are exactly the singular points of this algebraic variety. And it can be a feature in an application, like in a Netflix problem. It's good to know that you have even less profiles, but can also be a bug depending on what you want. So the message here so far is that in algebraic varieties, there are singular points, and they can be very important in an optimization problem like training a network. Such varieties do not have boundary points, but in the middle column, we do have boundary points, and they are important. And in the middle column, because of this full dimensionality, you cannot have any such singular points. So these two situations are in some sense really opposites from each other. If you have an algebraic variety or a semi-algebraic full dimensional object, sort of the points, special points that play a role in the one setting do not play a role in the other, and vice versa. So then we have the third column left, okay? And the third column is very interesting because it's sort of the first scenario where you can have both. So it's the first sort of geometric objects that can have both boundary points and singular points. And so both of these can a priori be important for the respective optimization problem. And that's what I'm going to talk about now, unless there's a question. I can already give
I have a question, if you don't mind.
Please go ahead.
Apart from understanding the geometry, let's say, of the space of matrices then that we can reach or have in this convolutional neural networks, do we have a full mapping between these two worlds, for example, either in terms of how distances distort from between two matrices in the convolutional neural network or 2 points in this algebraic variety, or for example, how dynamics in the real world translate into dynamics onto this kind of manifolds?
I don't think there is a full understanding. I think there are some things, but I think it should be easy in this linear setting to work out. I think it's just we haven't done it, and I think that there hasn't been too much work on this linear convolution thing, so I don't think it's fully understood. Yes, I can talk a little bit maybe after on pointing to some references. But yeah, it should be sort of not too difficult to do that. And of course, some things that we did work out, and not even, to some extent, on like the dynamics question that you asked, like what sort of invariant, what things stay invariant along gradient flow, at least to sort of that extent. But yeah, we don't have sort of the full structure written out, but it's a very explicit map, so you can do it.
Yeah. So do you have, for example, like natural like distances or metrics on this kind of varieties, or?
Yes, you kind of have some sort of natural Riemannian structure.
And do we understand how do they like how do they correspond to other natural metrics, for example, on matrix spaces or something?
As I said, in a linear convolutional setting, no, because we have not like worked it out. So I cannot. I guess I know that you can do it. Okay, well, like we as a community can do it. It should not be a too difficult problem. I just think that it hasn't been specifically done for these linear convolution settings, as far as I know. But for linear dense networks, there's like some very nice paper, I think from this year or last year, where this sort of whole story on the Riemannian geometry of these neural manifolds and other matrix distances is worked out. It's like a
thanks.
Holger Rauhut.
Yeah, okay. Well,
and some other co-authors.
Okay, yeah, thanks.
But for the convolutional thing, I don't know who's asking the questions. I don't see you. Okay, now I see you.
Yeah.
Hi.
Hi.
Yes. Okay. So, but very nice question. Yes, we have not done that. No. Very good. Okay, if there's no other question, I'm going to give you a tiny spoiler already in case someone has to run early. So essentially, we're proving that in many situations, something which I find very surprising, but maybe it's just me who finds that surprising, and it's supernatural, but this double question mark in this table, we can oftentimes show that it's almost never going to happen. So when you train a neural network, where there is boundary points and singular points present, but still for almost any choice of training data, you are not going to land in either of them, which is not true in the two columns on the left, as you see. So something is going on, which makes really these semi-algebraic low-dimensional sets. I think we are very far in the sort of math community of really understanding what it means to solve an optimization problem over semi-algebraic sets in general. And so this can be very complicated. Okay, so let me prove this to you, or at least show you the precise result. So we proved what I just said, specifically for the squared error loss, but I think you can do it for any sort of algebraic reasonable loss, and the result shouldn't exactly change, but to be able to give a concrete proof that is also readable, we did it for the squared error loss, which eats then such an end-to-end convolutional matrix and computes the loss. Okay, and then we want to remind ourselves that although this function small l here is defined on these end-to-end convolutions, if I run an actual training of a network and I run gradient descent, then I am going to do it on the parameter space, of course. And that comes back to the previous audience question, right? We sort of need to understand what happens when I transfer from the parameter space to the function space, and how critical points in the one world relate to the other, and things like that. Okay, so here is this theorem. Our theorem works if and only if, in fact, all strides of the network are strictly larger than 1. So this is very exciting. Yeah, so there seems to be a geometric fundamental difference for networks where all strides are larger 1 or not. So the other assumption here is n is going to be the amount of training data, and you can just think of this inequality as sufficiently large training data, where we can be precise what it means. And then I can say that for almost all choices of training data of that amount n, and now every single critical point of the loss satisfies one of the following. Either it is just, in fact, the zero function, so that's easy to check and kind of boring, or all the critical points that do not correspond to the zero function correspond to smooth, so non-singular and non-boundary points of the neural manifold. So that's a very strong theorem. Again, it says for a generic choice, a sufficiently random choice of data, sufficiently large data, then every single critical point corresponds to either a zero function or to a very much sort of non-special point on this neural manifold. So now this is what I can write here in the table. So on the right column, I can write that we're almost never going to land in the singular locus or on the boundary. And we can even add another tiny bit of information, which again relates to the question of how optimization from the parameter space and the function space is sort of related to each other. So I want to highlight this notion of spurious critical points, which is used in different ways throughout the community, but I am very strongly advocating for this way of using this word, because what I'm defining here is that a critical point in the parameter space, a theta, the parameter vector, okay, I call it spurious if when I actually look at it in the function space, it's no longer a critical point. But because of the fact that gradient descent works in the parameter space, the geometric picture you should have in mind is that critical points can sort of arise in two ways. They can either be honest critical points of the loss function that we sort of are interested in function space, or they can just arise from the way the network parameterization map works. Okay, and these latter ones, they are actually not really meaningful for the problem that we want to study, and that's why I call them spurious. And there's something interesting about these spurious critical points, because in sort of this vast literature on linear fully connected networks, they have been studied quite intensively, as I said, not necessarily always under this name, but they are present and they are causing problems. Again, let me refer to sort of this work by Holger Rauhut's group, etc., who attempted to show, for instance, that linear fully connected networks converge to global minima. And one problem that arises there is certain type of saddle points, which essentially correspond to these spurious critical points. So they are playing a role, and they appear in the linear setting, the fully connected setting. We also know from previous work that they often appear for convolutional networks with stride 1. And the theorem that I showed you on the previous slide also has this add-on that we can also in fact show that they almost never appear when all strides are larger 1. So choosing all strides larger 1 seems to be better for the optimization problem. So maybe that's something to consider, and it would be very exciting to see what happens when you try to do this theorem over like ReLU networks or something like that. Okay, so here is now the full version for sort of sufficiently random training data and sufficiently large data. Every single critical point is either just a zero function or a non-singular, non-boundary point on a neural manifold, and also is not going to be a spurious point, but really a regular point of the network parameterization map. Okay. So that is really, really cool. It also tells us this last yellow part, yeah, that optimizing the loss function in this situation does not pick up any extra critical points. So if I were, for instance, interested in counting how many critical points I typically have, then it's enough to count them on the function space, because there's not going to be any additional points in the parameter space. So that's something that I'm looking at the moment, counting those points. Okay, so that's, I think, sort of the main story. I could end the talk here or answer more questions. What I have on the slides left is looking at this boundary and these singular points that these function spaces have. I don't know how much time we have left. Is there a full hour scheduled?
Yes, okay. Sure.
Okay, so if there is not any immediate question right now, then I can continue a little bit. I want to go back to this picture that I showed you on the slides. And here is again, if you want one technical slide. So these two pictures, they compare two neural network architectures with each other. And you see in the picture that they look very similar. But the right picture is really the left picture, where I took this pair of scissors and I cut it off along this dashed line. And that's not just one sort of specific example or instance of this behavior. This is something that is generally true for linear convolutional networks. Namely, how did I do this? So let us maybe look at the very, maybe I can open a pen. If you look at this first equation here, what does this map do? It takes a quadratic polynomial and a polynomial which is, well, it's linear in x squared, so it's kind of something times x squared plus something. And then I multiply them together to get a polynomial of degree 4. And here I'm doing something very similar, because this factor is the same as here. But this quadratic polynomial I have split up into two linear polynomials. That's the difference, okay? And so there is a difference in these function spaces just due to the fact that if you have a, if I'm sending you a quadratic equation over the real numbers, then you might be able to factorize it into two linear real factors or not, depending on its discriminant. And that is that causes the change in this picture. And so this is the geometric intuition, and algebraically what's happening here is that I'm just merging these two linear guys to the quadratic one. I keep this the same. And now you can imagine that you do this in general. Now let's do this in general. When you have a linear convolutional network, what I'm doing here is I'm merging all the neighboring layers with the same exponent vector. Or in other terms, I'm merging all the neighboring layers whose stride is equal to 1. When I'm doing that, I'm just merging them to get a smaller network. Then that's what I call the reduced associated network. And that's exactly what's happening in this example. I'm just taking some of the polynomial factors and I sort of pre-multiply them to get a different network architecture. And so in terms of strides and filters, etc., this polynomial operation just means to merge those layers that are neighbors and have strides equal to 1. And you keep doing this, and then the strides are going to become larger. Yeah, and then you get then sort of, we call this reduced architecture. Now it's going to have less layers. And so there is some nice observation, which is that when you do this reduction, so the tilde is the reduced architecture, then the only thing that's happening is that the neural manifold can get larger. So this is sort of slightly counterintuitive maybe, but I am sort of having less layers and then I have more freedom in my function space. But the Zariski closure, so if I want to send you the smallest set that is a solution of polynomials via email, doesn't change. So if I go back to this picture, then the right picture is strictly contained in the left picture, but if I were to take the Zariski closure, they would be equal. And so if I'm interested in these special singular points in the algebraic sense, it's enough to study it for these reduced guys because they either way correspond to the same variety. And so there is like a nice theorem, which I'm just wanting to show sort of for the experts, if you want, that like what singular points are. And so what's interesting here is the second bullet point, namely that we can specifically describe the singular points of these neural manifolds. And it looks quite messy, but actually it is not, because what's happening here is that I'm saying, well, the zero function is always going to be a singular point. And then there's going to be a bunch of other functions, but all of them are in fact functions that come from smaller neural networks. And that is something that sort of has appeared in many settings in machine learning or like the neural network theory literature, like in lots of works by Nadav Kohn, where I mean, sort of the observation that the special points in neural manifolds often in fact come from architectures that are smaller. And that's what we prove here. So the singular points on the neural manifold is just the union of all the functions that in fact come from a smaller network architecture. So the set capital D here somehow goes over all network architectures that are strictly contained in the one I'm looking at the moment, if you want. So that's very nice that we can actually prove it here. And as I said, it seems to be, this sort of statement seems to be true in way more generality. It's just, I think, hard to give a formal proof in generality. And here's just a tiny add-on. if you want to compute this, you can compute this set D. It looks horrible for a human here, but this is like sort of a formula you could give to a computer, and the computer could understand this. Okay, so it's something computable. That's the advertisement. And then here is an example. So in this example that I've always shown, there is just in fact sort of one singular point, namely the blue pinch point. That's so that I have marked it in blue. So you can use the previous slide to convince yourselves of that. But it's just a point in this picture because it's like a low-dimensional snapshot of the actual thing, because I think the actual thing is 4 or 5-dimensional, so I can't exactly draw it. So there its singular space is in fact the whole vector space, but here it's just a point in this picture. Okay, and then last thing, is that it might be very interesting to think about the boundary, because in general, I would have thought that I will often land on the boundary when solving optimization problems, but in fact, we have proven that that's not the case for strides all larger than 1. But no matter, we studied this boundary. And here also we're using this technique of reducing the architecture. So on the left, I have the original architecture, original manifold. Then I have this orange inclusion into the reduced architecture. And then I have this yellow inclusion into taking the Zariski closure. And so I could think of that my boundary, that's why actually comes in 2 flavors. There's 2 types of boundary points, okay? Maybe there's boundary that comes from the left inclusion and boundary that comes from the orange inclusion. And so here's a formal definition, but that's just what I want you to think of, okay? Boundary appears sort of because I have these 2 inclusions of a neural manifold in its reduced version and then in its Zariski closure. And there's something interesting going on, namely the orange boundary points. If they exist, then you can easily see them. They would be here, this dashed line. So the dashed line would be an orange set of boundary points, and it has codimension 1, and you see, oh, maybe if I do optimization, I might often land on this boundary. But then the yellow type of boundary points, they are lower dimensional. So that's something funny in algebraic geometry. Yes? If you have a low dimensional semi-algebraic subset, then its boundary can be something very tiny. And so in fact, this blue point here is not just a singular point, it's also a boundary point you can prove. Okay, I think I want to now really end here and say that you can understand these boundary points and the singular points to some extent, but in fact, when all strides are larger ones, they're either way never going to appear. And as soon as you pick one stride equal to 1, then you could use this technique of reducing architectures to sort of understand what your critical points are going to be. Yes, and now that's it. Thank you.
Thank you very much, Kathlén, for this very nice talk. Are there questions from the audience? Maybe I can start with one. So it's nice that you ended on this slide, because I would like to ask, is there like an intuition of what this reduction means from a machine learning standpoint or from an architectural design standpoint?
It's a very good question. When we got reviews back for the paper, that's exactly a question that the referee asked, because we're mainly using it as a technical tool for our algebraic proofs. And as I said, I am not the machine learning expert in this paper. It would be more Guido Mantoufar or Matthew Traeger. But I think it does have an influence, because you can sort of, maybe if I go back to this picture, so what happened in this picture is that so that if you choose those parts of your network architecture where all strides are larger than 1, this sort of determines your space of functions kind of as it looks on the left. Now,
Mhm.
if you also add additional layers that have stripe 1, or you like split your layers into like stripe 1 layers or something like this, then you can sort of more fine-grainedly tune your network. Think of it like that. Oh yes, thanks for starting the recording again. So what's happening is that by at first only picking layers where the strides are all larger than 1, you can sort of essentially decide already on the geometry of the space of functions you're going to get. And then you can split your layers into stripe 1 layers to sort of fine tune the space of functions you want to work with by chopping off pieces, you know, but you're gonna essentially, I'm sending you an object and you're not, the only thing you can do is cut certain pieces off. That's sort of what's happening here. But then you cannot change the geometry in a too crazy way anymore. So I think it can have relevance for sort of design perspective, but of course for a huge layer to like understand this in practice is not so easy. But I want to point out that you can, in fact, you can compute. Like my student Vahiti has a very efficient algorithm, which is like recursive algorithm, who can compute these Zariski closures of these function spaces. So I can, for almost arbitrarily big networks, compute those now.
Yes, but still, it's very interesting that sort of introducing these lower strides, because I think looking at the filters, you're kind of you have a lot of very local filters instead of one very blobby, or how to put it.
Yeah, exactly. Maybe
And it's
like
interesting
that,
that exactly corresponds to cutting off things from the variety.
Exactly.
Yes, Yongsheng, you had a question as well, right?
Yeah, let me ask a question. So when you take the Zariski closure, you end up with a very big set here. So but if you take something else, let's say like is it possible to compare the two sets, the one let's say like some sort of Lebesgue measure kind of thing, because you would think that like those expressible using like a composition of convolutional filters should be like somehow much smaller than the combined layer.
You think, do you understand? So if you mean, if I can compare how much larger the Zariski closure is in comparison to the actual sets?
No, so you have a picture where like I think like you say like I think you take two networks and then you compose them, and then like the Zariski closure is the same as if you just sort of like okay, so but like so I think one thing about Zariski closure, it can end up being like a rather big set here, right? It's like,
but the dimension stays the same. So I mean, so these sets, these neural manifolds are nice in the way that they have a well-defined dimension, and that when you take this closure, that it is going to be something of the same dimension. It's not that all of a sudden. But yes, so at infinity somehow, yes, lots of things sort of can pop up.
So I'm thinking about like say for like say approximation theory, so let's say how expressive these sort of things are. So could it be that like one is quite small compared to the other?
I think it would be a very exciting question actually. So from an approximation theory point of view, I was thinking what one could try to do in theory. You could take, say you have a tiny semialgebraic set, but you could take an epsilon cube around it and then attempt to compute the volume. If you do that, that would actually give you a precise, and then you could compare like sort of how much larger after I chop off a piece, how much larger or smaller have I actually gotten? I think so that should be, I mean, there was actually a paper in the Annals of Math from colleagues of mine who was actually about volumes of semialgebraic sets or epsilon cubes around semialgebraic sets. So I think it's sort of technology that we very recently, like from this year or last year, we have sort of a way of theoretically doing it, and it would be exciting to apply it to these.
Yeah. Okay.
To these neural manifolds.